Three light springs P, Q, and R are identical. Springs P and Q are connected in series as shown. A downwards force T is applied to the lower end. Spring R is instead cut into 4 equal lengths and the 4 pieces arranged like so. The two connecting bars have negligible mass. A downward force F is applied to the center of the lower bar. The total extensions of the two systems are equal. The springs obey Hooke's law. Which expression gives T in terms of F? So, noticing the symmetry of the two systems, we could actually just focus on one spring up top with tension T, and then the other one with the quarter springs with a force F pulling down. This is because the ratio of the extensions would be the same in both. So the first set would extend the same way as the second set. So we can just compare these two systems just to simplify the problem. Now, an equation I love to use in NSAA and ENGAA is rearranging the Young modulus equation. So E equals F over A divided by X over L. We get F over X times L over A, which if you notice is the spring constant F over X times L over A. So rearranging this, we get an expression for the spring constant in terms of the Young modulus. K equals EA over L. So the spring constant is not technically a constant as it does depend on the dimensions of the material you're using, whereas the Young modulus is a more fundamental property of that material. So you could have two different springs that may be made of the same material, and they'd have the same Young modulus, but depending on how they're cut or their cross-sectional areas, you would have different spring constants for these. So K equals EA over L, very useful. So when you add springs in parallel, for example, you're effectively adding their areas or their modulus of elasticity, the EA term on top. So when you add two springs, K1 and K2, you're just adding the modulus of elasticity of each one. So E1A1 over L plus E2A2 over L, which is why you can add them in that way. When you add two springs in series, so if that was K1 and K2, you're effectively adding the or increasing the length. So it would be E over A, or EA over L1 plus L2. So this is at least a way you could see it. It's usually easier seen with similar materials or ones that have the same Young modulus. But you do get similar equations thinking in this way. So instead of remembering formulae for how to add them in series and parallel, I always tend to just look at this formula for spring constant, EA over L, and seeing what's being added or what's being increased in this term to get the effective spring constant. So, and if you notice, this is 1 over K equals 1 over K1, which would be L1 over EA, plus 1 over K2, which would be L2 over EA. So 1 over this term would equal 1 over K1 plus 1 over K2. And that's how you get this formula. So going back to the question, we know that this would be K. So the extension would be T over K. Whereas in the other ones, we've cut them into 4 pieces. We've cut R into 4 pieces. So the length is 4 times smaller, which means the effective spring constant of each is 4 times bigger. So that's 4K and 4K. Looking at that EA over L term. So 4 times smaller natural length, 4 times larger spring constant. Now if you notice, then we've got the two springs in parallel. So that means we're essentially adding the two areas, if you want to think of it in that way. So the effective spring constant would actually be 8K. Given that the extensions of the two systems are equal, it says in the question, we can now compare these. So we have, going down, we have t over k equals f over 8k. And it's very easy to see here that t is equal to f over 8. So the answer is B. T equals f over 8. Hopefully you found that useful. Using k equals E over L can help simplify so many questions in NSAA and ENGAA. Instead of remembering the rules for how to add springs in series and parallel, I tend to find this is quite useful, at least giving some insight into how these equations work. If you have any questions, let me know in the comments.